he said exactly how it went. So thanks for the opportunity and for the call. This kind of calls give the chance to other people to talk. All right, so I will share my screen. All right, so yes, so I'll talk about deblurred images with mathematical models. So let me start by, you hear me well, right? Yeah. All right, so yeah, let me start by motivating the image deblurring problem. So here I have an image of tissue that you can obtain by looking through a microscope. And so it's not, the minute that you have a lens, so you are going to have some blur. Going to a different dimension in the sense that maybe we use a telescope, right? And we are looking at the sun. Again, we are going to have a lens that is part of this telescope. We can have medical data, different machines, right? But again, if there is some part of the instrument that will get this blur that we would like to, get rid of somehow. I put this one here, which is actually a project that I did when I was in graduate school, one of the summer workshops at the Institute of Applied Math at the University of Minnesota. And the problem was to do reverse engineering, right? So the idea was to take pictures of a chip, although much more smaller than what we are really seeing here. But that was the problem. So you take a picture and you want to do reverse engineering, but the image was also blurred. So again, different examples, again, astronomical images. Maybe when we went on vacation and we took a picture and you moved, and that's all, your memories. And then what can we do to recover, right? So basically what you have is the image, and there is no other way to improve it, right? You cannot take the picture again. But let me emphasize that our approach here is to use math to enhance these images. Again, we might not be able to go back to take a picture during the vacation, but also the minute that we have an instrument that has a lens like the telescope, even if we take them outside of the Earth, right, outside the atmosphere, and we put it in space and we make them huge, there's always going to be this lens that it's going to produce a blur in our image. So, even though we do improve our instruments, this problem is going to be there. And the idea is to do math to improve and test these images. All right, so let me start by showing you how you go from an image to vectors. So this is a picture of my son a few years ago. He was 2 here and now he's 5. So, I'm going to zoom in, right? So I'm zooming in, but I keep zooming in until I have the pixels, okay? And in the computer, each pixel represents, is a number, okay? So the color of each pixel is represented by a number, actually by 3 numbers, but I don't want to get there. So I want you to think that an image is really a matrix, right? So each pixel that has a color really becomes a number in a matrix. And something that we can do is to stack this matrix, vectorize this matrix, which means that I'm going to take the first column of this matrix, I will put it in the vector, then I will take the second column, put it below, and so on. Right, so I can really think about an image as a vector. Of course, you can imagine that if this image is 1,000 times 1,000, this vector is 1 million size. Okay, so we are going to see that the system of equations that we see will introduce are going to be large, very large. So how can we do things in the computer faster? That's kind of our goal and things that I keep in mind developing all the mathematical tools that I will talk today. So how do we model this problem? So I will assume that this is really the true image that I would like to reconstruct, right? So I'm assuming that this has no blur. This is what I would like to have, but it went through a process. So it's like, first I will model how this process goes. So I have this image that you can think that it's a vector, right? When I talk about here x2, I really think about the vector that represents this image. But then it got blurred, right? Which means that somehow each pixel, right, got somehow a sum or information of the pixels around. And here you can see I'm using what is called a Gaussian blur, right? So the pixel in the middle, or one pixel, is somehow gets weighted with information of the pixels around. Okay? Now this process or this operator, what happens to this image, can be modeled using a matrix. Okay, so in this case, we are assuming that this process is linear. So if it's linear, there's a matrix that will take us from this image or this vector to the vector that represents this blur image. Okay. Now, in reality, we don't have just this blur. In reality, we have a blur plus noise. Okay? When images, when the cameras capture an image, actually the electrons are going not exactly where they're supposed to go, so there are extra errors that are in the image that we have. Okay. So this is called the forward model, in the sense that we are trying to model the whole process, okay? Going from what will be the true, what happened to that image, plus the noise. Okay? And we can model that as a system of equations. Now the problem is the image deblurring problem, which means that given an image, this blur and noisy image, we want to reconstruct this image, right? The image that we call x2. Okay? This will become our unknown now. Okay? So we are going to assume that the blurring process is known. So we assume that the matrix A is known, and we will assume that this is data, that we know this blur and noisy image. And again, we are going to try to solve this system. Okay, that's the problem. Bueno, so when we will say, well, it's just the inverse, right? So we will do the inverse process of saying, well, if we have the image A, and if A is invertible, we just, solve this system, and then we get a surprise. When we try to do that, we obtain an image that is even worse than this blur. This blur, maybe we could kind of guess that there was a face there, but now it got really worse. And it's like, what happened? So the image, I will talk a little bit more to understand what is happening here, but the image deblurring problem is an ill-posed inverse problem. When we have a system of equations like this one, but when the data gets a little bit of noise, it gets perturbed a little bit, then when we try to do the inverse, those perturbations get enlarged, and then it contaminates all our solution. So again, this image deblurring is part of a whole family of problems. So many of the things that I will talk about today can be applied to other problems, similar problems. But it's nice to use the image learning to explain these kind of problems. Okay, so I want to understand this problem a little bit. I'm going to use a mathematical tool. I'm going to use what is called the singular value decomposition to understand more about why everything goes wrong, basically. What is this tool? Well, the singular value decomposition writes the matrix A as a product of three matrices, U, sigma, B transpose, where they have very specific properties. Sigma is a diagonal matrix with all its entries are positive numbers, and they are ordered in decreasing order. The matrix U and V are orthogonal matrices. And when you write the U transpose U or V transpose V, we get the identity matrix. Right? So you can think about the columns of this matrices U and V are all orthogonal vectors. Right? So when we do inner products between any two columns, we get one. So they are orthogonal, but also the norms of them are one. All right, so let's see how we can use this. So what I'm plotting here are the singular values of the matrix A. So, I didn't actually say, let me go back for a second about the names. So these entries here is what we call the singular values. Okay, so I'm going to plot them. So here I'm assuming this is a matrix more or less 1,000. Okay, so I'm assuming here this is a matrix 1,000 times 1,000, which really in the kind of problems that we want to solve is going to be like millions times millions. But this is a small problem to explain. So suppose that you have this matrix, so A, and I'm plotting here the different indexes, right? So the first element in this matrix sigma basically is going to be 1. And then the second element is going to be close to 1 and so on. So these are the values of the singular values. Okay. And we plot them this way so we can see how they behave. Okay. We know that they are ordered in decreasing order. Okay. This is, we know this happens for all the matrices because the decomposition is built that way. But what is important here is that there is no gap, right? So we have these singular values that decrease, but there is no clear gap where we can say, oh, I can separate the singular values in some clusters. Okay? And this is typical of this kind of problems. All right. So now I'm going to, what I'm trying to plot here are the columns of the matrix V, just to give you an idea how they look, although you are seeing this and where are the vectors, right? So you are looking at images. But these are actually so remember what, at the beginning I have an image and I vectorize this image, right? So I went from an image to a matrix, but then this matrix I make it a vector. So the columns of the matrix V are vectors, but then I'm doing the opposite. I'm converting them in matrices, and I'm showing you the image of those matrices. Because, well, you will see later on, I want to keep working or keep thinking about images because that's what we have. Okay? But again, this is related to the first vector, the first column vector of our matrix V. You can see that it's very smooth in the sense that it's going from white to black in a very smooth way. when this is related to the first singular value, then this is related to the second singular value, and so on. So when the sigmas or the singular values are decreasing, okay, we see that these vectors get more oscillatory. Okay. The change between white and black start changing more and more. Okay. But we do have that relationship which is related to this problem. The largest singular values are related to the smooth singular vectors, and the smallest singular values are related to the high oscillatory singular vectors. All right, so what let me kind of summarize in this slide the characteristics of the problem that, or the system of equations related to this image deblurring problem that we are trying to solve. So again, we are going to have a matrix and a right-hand side. The singular values of this matrix decays without a clear gap. We are going to assume that this noise that is there is a Gaussian. Okay, just imagine, some perturbation around the zero, plus minus, something very small. And oh, Queen is a statistician, right? Or I don't know, but I hope I didn't simplify this too much. This idea of Gaussian noise. Okay, so singular vectors become more oscillatory, and there is another property that says that if we write our right-hand side in this basis given by the singular vectors, we can see that they decay, these are the red ones, that they decay faster than the singular values that are in blue here. And we will see why that is important. Here, the black are the noise. So the noise, even in any base, will be more or less the same. All right. So what I want to do now is we talk about x as the A inverse times B, and we can, because we know the singular value decomposition of A, we can write that using the singular value decomposition, right? So again, what we call the naive solution, this solution that is actually bad, but right now we are trying to understand why is it bad. So we use, basically what I'm doing here is to write the solution as a linear combination of the singular vectors. Okay. So here, this is a number, so let me go a little bit through this, but this is a row vector times the right-hand side is a column. This is kind of an inner product. So this is a number divided by number. So these are coefficients, these are numbers, okay? And these are vectors. Numbers, vectors, number, vectors. So we really have a linear combination. We are writing our solution as a linear combination of these particular vectors. So I'm using an example, right? And I'm going to here compute who are these coefficients. Okay? So we have the coefficient that is related to the first singular vector that we saw that it was smooth, and then this one is the second one, and so on. And here I plot the last one, and we see that this number here is huge. So when we try to understand this solution, and we write it as a linear combination, we see that this term is the one that really dominates. Right? And it's clear now why we have this so oscillatory image, because really that is kind of these terms, right? So huge terms that go with these very oscillatory images. So let's try to understand where these coefficients are coming from. So what I plot here are basically those coefficients, except that because I'm using a toy problem, I'm trying to understand, I know what is the true component, only the blur component and the noise. Okay. So again, I'm splitting each of these coefficients in the ones that have the V2 and the ones that have noise. And you can see this is the one that has just the V2, and this is what happens with the noise part of it. Okay, but here I'm going to use this Picard principle in the sense that we saw, or we said that the V2 decays faster than the singular values, which means that even if the singular values are going, to 0 or getting so small, the part on the top is going to be smaller, right? So they basically, these terms, the part corresponding to V2, are getting smaller faster than the singular values. But what will happen with the noise? Well, the noise in principle is all, it doesn't matter in which base it is, it's really the same, it's like constant, right? But then we are dividing that constant by something that is getting smaller and smaller, which means that those terms are going to get larger and larger. Okay. And again, and at some point, basically, they are so big that they dominate the solution. So the idea is, how can we filter this out? And that's basically what we are going to do. We are going to incorporate in this linear combination, in each term, we are going to incorporate weights, okay? A weight where we basically want to eliminate these terms that are not really useful, okay, and are contaminating our solution. So this is the idea of filter solution. Basically, we take exactly what I said, the linear combination, we add the weights where it's going to be close to 1 when the singular values are large, where still we have good information, and then 0 otherwise. Two very standard known methods is the truncating SVD. Basically, we are going to say 1, give weight 1 to the first k terms, and then 0 otherwise. So that's basically like keeping the first k terms in this sum. Or another very known method is called the Tikhonov Regularization. We are going to give these terms, these weights that have a very particular form, but they still behave the same way, in the sense that for large values, these, we will assume that the lambda is a little bit smaller. So these basically are 1s, but when they get very large, very small, this will go to 0, and we will not be divided by 0 because we still have this lambda. Okay. But the same idea, different weights. Now, I want to talk about this Tikhonov regularization a little bit more. Yes, so we are looking at this as this linear combination, but there is another way of looking at this solution, which is this minimization problem. So the solution obtained this way by incorporating these weights here is the same as minimizing this function here, which has a fitting term, which basically is saying I want a solution that fits the system of equation, ax equal b. Okay? But we are now incorporating another constraint. What is this constraint? Well, here in particular is saying that we want the solution to be small, the norm of the solution to be small. So let me go back for a second to my example. Oh, many slides back. But here, if you want to compute the norm of this vector, it's going to be huge because of these terms. Okay, so trying to enforce that the norm of this to be small somehow forces the solution not to have these large coefficients. Okay. So now again, the nice thing about rewriting this or rethinking this problem as a minimization problem, let us think about how to extend this to extend this in the sense that now we can add different constraints. For example, notice that here instead of having the identity, now I have another matrix, and this matrix could be the discretization of the derivative operator, right? So I could incorporate a constraint that says I'm looking for images that fit the system, this blurring process, but I want the solution also to be smooth, for example. Again, by incorporating these constraints, we are somehow filtering out the noise, but also looking for obtaining good images or images that have characteristics that we desire. By the way, I have my son next to me playing around. Okay. I don't know if you can hear him, but I can. All right, so how important, so notice here that there is a parameter, right? That, for example, here when we said, oh, we are going to incorporate the weight, we have this lambda, but here in the minimization problem, the lambda is there. So somehow we are saying, yes, we want to incorporate this constraint, but we give a weight to this extra constraint. So how important is that parameter? So here I have an example. I'm going to vary this lambda, and for each lambda, I have a different minimization problem. So for each lambda, I have a minimization problem and a corresponding solution. So I'm plotting the corresponding solution. So I start varying the lambda, and you can see that it affects the solution. And at some point, you can see a little bit more, a little bit more, a little bit more. And then at some point, it starts getting too blurred or too smooth if we are asking the solution to be smooth, right? So there is a balance. We want to filter the noise, but we don't want the solution basically be this only constraint and not fit the system of equations. So many ways to choose this parameter. For example, you can use what is called the L curve. Again, for each lambda, you have a minimization problem and a solution. For that solution, you can compute the two norm of the constraint, and you can compute the norm or the fitting term, norm of AX minus B. And so these are numbers, right? So we can plot in R2 that combination, and we will see that, again, if the lambda is very small, then it will try to make this term small, or the opposite, let me think. Yeah, I think it's the opposite. But you can see that, you know, we have different combinations, and the lambda that we would like is the one that makes both small at the same time. So it will be the corner of this L curve. Other methods to find those parameters, but I'm going to talk about one today that you can obtain about learning, like from data. But before I tell you about that approach, let me give you an idea where is this coming from. And basically we are using this what we call fitting, right? So imagine you have data, right? So here this is X and Y, so I have points X, Y, and this is the notation to say, oh, this is my data point 1, my data point 2, data point 3. And what I want is to find a curve that actually or this line that actually goes through 0, right? That is going to fit this data. What does it mean? Well, I want to find the line that makes these errors as small as possible. Okay. So different way of saying the same is we want to find a line that that when we put the new value x, it will give us a prediction, okay? So I want the prediction and the data that I have to be as small or as close as possible. Okay, so yes, so I'm writing this, right? So we want this all together, right? So we want to have the prediction and this is our prediction and the data as close as possible in all of the points. Okay, that's why we have this sum. Okay, so this is graffiti. Sounds familiar. But I want to think of this a little bit different, but I'm going to rewrite it just a little bit, which means that, which is basically, I want to write this as I'm going to minimize, again, the prediction minus the data, where the prediction is given by this line. Nothing strange here. All right, why I want to write it this way? Well, because now I'm going back to our problem, and I want to assume that I have training data. In this case, are training images. So I have images that we know that are true. Then I have these blur and noisy images. So I will assume that we somehow have that data. And I want to find lambda such that this Tikhonov solution and the true data are close. Of course, before we have the least square and we were just having numbers. So now we have to incorporate norms, right? Because now we have vectors. So we want these vectors to be close for all of these images. Now, the prediction, in this case, is not just coming from a line, it's coming from another minimization problem, right? So our Tikhonov solution, that is a kind of our prediction here, it is coming from this minimization problem. Okay, so I'm talking all these ideas of this work has been already published. So there is some references here. So this is called bilevel optimization problem. We are trying to minimize this, basically the errors, subject to another minimization problem. And it's bilevel optimization because we have two minimization problems involved. Many here I'm citing 3 papers where they are using basically these ideas to find the regularization parameters. All right, so in particular, in this case of Tikhonov regularization, there is a closed form, okay? So we don't really need to have the 2 minimization problems. Once we know that this minimization has this closed form, we can incorporate it in the what will be the outer minimization, right? The one that minimizes with respect to lambda. So we can really just look at this minimization problem. All right, to understand a little bit more, because here we have this matrix L, I'm going to use another I have a visitor. Sorry, I'm giving a talk. Can I give the talk? So I'm going to use another tool, what is called the generalized singular value decomposition, which is this joint decomposition of A and L, right? So before I mentioned the singular value decomposition that only is a decomposition of A. But because here we have A and L, I want to have something that relates them. So why I'm talking about this? before we use the singular value decomposition to understand what was the problem, why do we have this bad solution? Here I'm actually going to use it to rewrite and simplify our minimization problem. So I'm keeping a little bit some details, but basically we can write this Tikhonov solution as a linear combination in a basis given by this generalized singular value decomposition, okay, which is different from the singular vector of A if L is not the identity. Okay, so it's a different basis, but really it's similar in the sense that, again, we are writing the solution as a linear combination with certain weights. Okay. At the end of the day, you have this minimization problem that is easy to solve, right? So we are taking some time, right? Getting the singular value, the generalized singular value decomposition is not cheap. But once you have it, this problem of finding the lambda that fits all these training images is easy to solve. All right, so some numerical results. This is just for 1D deconvolution, which means that even here we have images. We are going to really look at signals. So we are going to take 200 columns of each of these MRIs, okay? And use them, this is like the true images, and we are artificially going to blur them and incorporate some noise. And we all also know the level of noise, but we don't know so basically our training data is going to be these signals, the 1,000 signals, and then the blur and noise. And we are going to use this L, which is the first derivative operator. Okay, so here you can see that, well, a few things. Here that is the optimal Tikhonov singular value decomposition. Here I'm assuming that the matrix L is the identity matrix. That's why we have the singular value decomposition. I want to compare that with incorporating a matrix L, the first derivative operator. And then, so here the filters have a very nice structure as we saw. So basically we really need to find the parameter lambda. But here we are also comparing to what is called the optimal error SVD, where actually we are leaving all these weights as parameters, right? So we are trying to find all the weights that makes this training or the error small. So just to repeat maybe that part, here we are trying to do this training process where what we are trying to find is just the lambda, okay? And here we are doing this training, but where each weight is an unknown. So we are trying to find the best weights, much more work. Okay, so here, what I'm plotting is we find those parameters using these minimizations. So once we found them, now we test them, right? So we have the same process to get the training data, we do to get some validation data. So we want to see how our parameter is doing in these new sets, right? So again, I like to repeat, but we found all these parameters using some training, okay? And now we are going to use this Tikhonov and these formulas here, but with parameters that we already found with the training, we will use them with validation data. So, and these are the errors that we obtain. So, and this is the mean, and then you can see how this error varies. Okay. but when we go here, we see that basically in terms of errors, using the matrix set that is the first derivative operator and only finding one parameter is enough to then reconstruct or have good reconstructions. All right, some more plots and numbers to give you an idea that this method is working. Actually, I wanted, let me see. Yes, so I wanted to say a few more words about other projects I have been working on. But let me just conclude that part. Basically, I hope I convince you that this is actually a difficult problem, right? It looks like we can just invert and we will, a system of equations, but then there is all this, the noise gets into the solution. So it's not a trivial problem, even though when we write it, it looks like, oh, this should be easy to solve, and then it's not, okay? And we have used a lot of numerical linear algebra or linear algebra tools to understand and then to solve it. Okay, so if you are taking linear algebra, here are a few, many applications that we have used. Okay, so I want to mention a few other projects that I have worked on. This was my first job as a mathematician. I worked as an actuarial assistant, okay? And I'm from Argentina, so this was in Argentina. And here we were trying to price health insurance. Okay, why do I want to also mention about this problem? You will see in a few slides. So this particular problem was we needed to have an estimation of the HIV incidence in all the ages, but we only have that information in groups, right? So what we would like is, so these dots here are given information, but we really would like to say, if someone is at age 25, it will be nice to know, what is a better approximation. We would like some prediction. Okay, so this is again curve fitting, right? So, oops, oh, I don't have my curve. Maybe I just got that slide. I know, maybe, let me see, no, it's here. Okay, so, well, you have polynomial interpolation. You can assume, that the curve will go through those points, and then you solve a system of equations. That might not be the best idea, right? So then what we do is to find something that basically fits the curve. But, okay, I'm going kind of fast here because, what I want to use this example is to show you that at the end, you are going to solve minimization problems that are similar to what we have seen in image deblurring, okay? This one doesn't have a regularization term, but maybe it might be a good idea depending what curve or what are you exactly looking for. But my point here is this is a different context, but we have a similar problem. And I want to give you one more problem. When I was a graduate student, I did a summer internship at the medical school. I worked with Gabriel Kremer, who is a biologist. And we look at the object recognition problem. So let me go through it a little bit. So what is this problem? The idea is trying to understand how we see, so we can tell the machines how to see things or how to recognize. So this is the experiment. It's basically, you put electrons in the head of a person and you show pictures, right? So for example, here we show a car and then we measure from the different electrodes, we measure these signals. That basically, actually, these signals are basically vectors. Okay, so the data you are getting are vectors, and you can put the vectors, stack them. So have a huge vector that represents, let's say, this picture of a car. You show different images. Every time that you show an image, you have a vector, right? So we are getting some data. And the idea is, what we would like is to find, classify, right? So if someone shows cars or shows shoes, we would like the machine to differentiate them. I'm going very fast, but I'm using this only to just to show you something. But the idea here is how the machine can classify, and basically giving points, right? I mentioned these are really the data. You can think about this image, replace it with the data that you had, that are this huge vector with the electrodes. Okay? So with that information, you say, okay, now I want to find a line that separates this point in space. I'm not explaining this video, but hopefully you get some idea. But I want to get here. How you get this line in space, giving this training data. At the end of the day, you are going to solve the problem that we use for image deblurring. Totally different problem, totally different data. And at the end, the mathematical tool that we use actually is the same. Okay. And okay, I went really fast through this, but that, I wanted to show you a few problems that I worked before actually working in the deblurring problem. Different area, different questions, and at the end of the day, the math was very similar. Matrices, vectors, norms to write these minimization problems, and then the minimization problem and the tools that I need to solve these minimization problems are the same. So I think I will stop here.
All right, great. Well, let's virtually anyway thank our speaker. And are there any questions?
I have a question.
Yes, go ahead.
This is Nicholas Dwork. Thank you for a brilliant talk. Two questions. One is, in your experience, how much training data do you need? And then another question is, have you worked on non-differentiable regularization functions other than Tikhonov, like L1 norm?
Mm-hmm. Okay, good questions. Actually, I took one slide where we show, so basically, if the space where you are looking for the solution, right? So I talk about the SVD and L being the identity, or L being the first derivative. But then, depending what L you use, then you have your solution. You can write it as expansion in a particular space. If that space is good, then you don't need that much training. Okay, so it's like, again, if you are already looking for the solution in the right place, you don't need so much training. Right? It's always a balance, right? In the sense of degree of freedoms, etc., or assumption that you incorporate. So if you have more extra information, then you don't need so much training. And the other question was, yes, so if I have used, so instead of the 2 norm in the regularization term, right? So I have the fitting term, I use the 2 norm there, and the 2 norm in LX. So if you change that by the 1 norm, then the problem is not differential anymore, and that's the question that Nicholas is making. And yes, I have used other methods that actually, there are some tricks that trying to solve the 1 norm, you can transform it in the 2 norm and still solve basically the same problem. It will be more expensive because that transformation then might add extra steps in the middle. So it's going to be always more expensive, but you might get better solution if your image that you are trying to reconstruct has sharps or is sparse. It depends. Yeah.
Yeah, Malena, I have a quick question.
Mm-hmm.
So thinking about the actuarial application you mentioned relating to the life insurance work, my research is in PNC, and I'm thinking about an example where, you know, these days insurers let people to take pictures of their like accidents, and something I'm thinking about is there a way you could transform this vectors from these pictures into maybe like a single number or a scalar, then you can use it into a reserving model that could help to predict reserves.
Yeah, so so basically you are trying to use your images, reduce them to get some useful information, but reduce the dimensions, right? Not sure if you will be able to reduce it to 1, but definitely, yeah, that's what many people do, right? So you have MRI images of the brain. I mean, in many contexts, we have images, right? But it depends on the problem. We want to reduce the dimension. So again, it depends on the problem. I haven't talked about other problems that I have worked on, which was medical diagnosis. And we have exactly that, MRI images, and what we did is specific measurements, right? So we went from a whole image to have only 9 measurements. This could be the same, right? It depends on the context. If it's an accident, somehow you could think about, okay, what is the relevant information and reduce that in that sense, yeah.
Other questions? So maybe I'll ask one real quick. So you had this you have this penalty term, right? And so you were using L, so you were basically penalizing sort of jumps in your reconstructed image. But you're looking mostly at sort of, if you're looking at this MRI data, right? Do you lose sort of definition in your picture because you sort of expect some edges, right? I mean, you sort of expect some jumps from black to white, and penalizing those, do you get sort of smoothing in the reconstructed image?
Yeah, so great question. There is always a trade-off, right? And it goes back to what is your problem, right? And what is important for your application. Yeah, so yes, the 2 norm makes things, we were able to rewrite this and use the generalized SVD because we were using the 2 norm, right? So we made it super fast to solve, but on the other hand, we lost the edges and all that information. Yes, so you can go to the L1 norm, for example, or other formulation or other regularization terms, but it will probably make it more expensive. Always a trade-off of the speed that you need and the accuracy that you want. Yes.
All right, any last questions?
I don't, so I haven't done this kind of work before, so this is probably a stupid question, but I'll demonstrate to students that there are maybe stupid questions. When your singular values were big in the highly oscillatory range, is there a notion that that's artifact of how the problem was vectorized? Is there, if you went through the data on different slices, would you distribute the oscillatory nature into different parts of the basis, or is that a stupid question?
No. I tell you, no question is a stupid question. All the questions are good, are important. So good question. this is related to the process. So it's not related to the solution. So this is a property of the matrix. Okay, so all these matrices are going to have that property. So you cannot get rid, you might be able to use different lenses, right, and control how much blur your lens is producing, okay? But not in terms of taking some rows off, or yeah. So yeah, so, but let me clarify. Again, these are inherited by the problem itself, right? So we talk about the ill pose of the problems, right? So even if we try to do other things, those are, even if we write them in continuous forms, those are things that are proper of these problems itself.
All right. Well, if there are no further questions, let's thank our speaker one more time. Thank you so much for joining us. And as a reminder to those folks who are here, we will have, next week we'll have Dr. Trina Palmer from Appalachian, and she'll actually be talking about her work on her OCSA last semester. So thank you all for joining us, and we hope to see you in the future. All right.
All right. I hope.
All right. Thank you so much.
Bye.